Okay, let's get into it. Glad that you made it. Um, so on Friday, there's two things happening. You're submitting the homework assignment before 1 o'clock, and then we're having the exam. And regarding the exam, I've mentioned before that you can bring a page of notes. And so you should look through the assignments that you've done. You should look through the in-class exercises that we worked together and prepare that to use as a reference during the test. And I'll provide the periodic table. You don't need to bring your computer. I'm not going to have you use Excel for the exam. It's just going to be hand calculations, and so you should bring your calculator and obviously a writing utensil and so on. And then the wastewater treatment plant tour is scheduled for the 12th, and there's a chance we may also go to the water treatment plant, and we do that in April. So I'll provide more details about that when it's all settled. Regarding the test, I wanted to show you this from the course schedule, just to identify the topics that are going to be included on exam 1. So this schedule just shows for each class meeting what we talked about, what is the book chapter that goes along with it. And so you can see it's chapters 1, 2, 5, and 6 from the book. And then the homework assignments that apply. And my intention, although I haven't finalized the exam yet, my intention is that concept questions are going to comprise about 30% of the points that are available. And so those will be me asking you to explain certain concepts, or it's not going to be true, false. It's not going to be matching. It's going to be looking for a level of comprehension that you're explaining a concept. And then about 70% of the points will be related to problem solving, answering a question numerically, doing calculations, that kind of stuff. So does anybody have any questions about the exam? All right, so we'll do that on Friday. Let's just take a step back and refresh our memory of what we've been talking about. We're talking about water treatment, and water comes from either a groundwater source or a surface water source. And groundwater is relatively easier for us to treat because it's not been in contact with as much like human materials, and so generally groundwater doesn't have the same bacterial concerns or viral concerns. Groundwater doesn't generally have turbidity because the soil itself is acting as a filter. And so it's surface water that's generally a little bit trickier for us to treat. And one of the main things that we want to remove through the drinking water treatment process is turbidity. And here's a series of jars that's showing an increasing level of clarity or a decreasing amount of turbidity. And even after the coagulation, flocculation, and settling process, there's still more turbidity in the water than we would prefer. And it's more than just an aesthetic concern. The turbidity harbors bacteria, and we're not able to kill bacteria that's fully embedded in a colloid particle on all sides, because you could put it through chlorinated water and the chlorine can't get to the bacteria that's surrounded on all sides by a clay particle. And so when it gets into your stomach, it has the potential to get you sick if that turbidity is still there. So typically as the water comes off the top of a clarifier, it may have turbidity between 1 and 10 TU, turbidity units. And the way that they measure that is they just shine light through a sample of water, and then they measure how many of the photons that went into the sample of the water come out. And so it's a scale that just indicates the number of free floating particles that are in the water intercepting light. So what we would like is for the finished water that comes out of sand filtration to have less than 0.3 turbidity units. Because if the turbidity is that low, then chlorination is effective at protecting us against illness. So the water that comes out of the top of the clarifier The particles that are still suspended are very small, but, and that's actually a bad thing, that they're small means that they're the ones that got away during the settling process. The big ones that settled quickly, they settled out very fast, and so the small particles are harder to remove, and so just giving them more time in the settling basin may not do the trick. So we have to try something completely different. But destabilized means that they still have the negative charge on the outside of their particle being suppressed because of the coagulants that we added to the water. And so we're not maybe going to be able to get them to collide with each other because there's so few of them. You know, if the turbidity is relatively low, then that means there's not very many particles remaining. And so colliding them and causing aggregation and settling is less likely as the concentration of particles goes down. But because they're stabilized, we are going to be able to remove them through sand filtration. So today we're talking about filtration. And what you think of as filtration is different from what I mean when I talk about sand filtration in drinking water. It's a separate process. And so traditionally when people hear about filters, what they think of is the process of straining. And that is simply that you are taking a fluid through a porous media, and the particles that shouldn't be in the fluid anymore get trapped on the porous media. They're strained out because the size of the particles is larger than the pore size on the porous media. So taking an oil filter as an example, you know, you recirculate the oil through an oil filter to try and remove the tiny little microscopic shavings of the engine particles. You know, as the cylinder's pressing, as the piston's going up and down through the cylinder, it has the risk of removing some of that material, and we want to get it out. And so this the filter that you use in a car is trying to take the particles out of the fluid. And so if you were to do a cutaway of that oil filter, it's essentially a fabric where the opening in the holes of the fabric is very small, and it allows the fluid to go through, the oil, but it traps any of the little metal particles that we don't want circulating and causing further erosion and scour of the engine parts. And so, you know, if you strain out the particles, then that's improving the performance of the engine. But the problem is that you have to have a very strong pump to force the oil through the tiny little pores on the fabric filter. And where you've got plenty of power available, like in a car engine, the amount of power that you're using to force the oil through the oil filter is just a tiny fraction of the overall power that the engine is generating, and so it's negligible. But in water treatment, if we were supposed to use straining to remove the remaining suspended particles, it would use an enormous amount of power. So it's not practical for us to use straining in water treatment. So straining is something that we associate with filtration, but there's other things, other processes that sometimes people call it a filter. So maybe you've seen these Brita water filters that people put into their refrigerator. Have you ever seen, they've got like these little carbon, granular activated carbon filters, as they're called. But what that really is doing, it's not straining the water, but as the water goes through the activated cartridge, activated carbon cartridge in there, then any of the dissolved chemicals we're trying to remove are preferentially attracted to the carbon in the filter. And so that process is the process of adsorption. Impaction and adhesion is what we're talking about today. So that's a really important pair of words that you should commit to memory in case it comes up in a couple of days. Impaction and adhesion. And so that is what I mean when I say we're sending water through a sand filter in surface water treatment. And so this little diagram, this is showing the sand grains. And sand, when it's packed on top of each other, there's going to be voids and then there's going to be the particles themselves. And this is exaggerating the size of the voids just to make it easier to see and understand what's happening. I mean, in reality, the sand grains would be more closely packed than they appear to be here. But the overall concept is that we've got some suspended particles in the water, the colloids, that are destabilized, but they're so small we couldn't remove them in settling. And so those destabilized particles, we send them through the sand, and if you look, the particles are smaller than the voids in the sand. Like it's possible that that particle, if it wasn't destabilized, it could just go through the sand, no problem. Because this actually is a good representation, although this isn't necessarily to scale. The point that I want to make with this diagram is that the particles we're trying to remove are much smaller than the voids. The voids are like giant caverns in compared to the size of these little destabilized particles. And so you may be wondering, like, how are we going to remove these little particles if the voids are so big in comparison to their size? We're certainly not going to do it through straining. Straining wouldn't work because the particles are smaller than the pores. And the way that straining works is when the particles are much larger than the pores. So the way that it works is that this destabilized particle is traveling through the sand, and eventually it will encounter a sand grain that's right in its path. So it's moving down through this column of sand. It may be several feet, the thickness of sand that the water's traveling through. But as it's moving, it'll collide with the sand particle, and it'll stick to the sand particle because it's just a collision right on the front face of that sand particle, where maybe it grazed a couple of others or close calls along the way, but eventually it will encounter a sand particle where the destabilized clay that we're trying to remove from water gets stuck onto the sand. And the same is true for all of the little sand particle, or excuse me, all the colloid particles that are in the water that we're trying to remove. Is just statistically speaking, as those particles go through the sand, they're going to encounter a sand particle that they collide with. And that sand particle, maybe it's not even completely clean. It may already have some other destabilized particles that are stuck to it. And so then it'll definitely stick to those other particles as well. So that impaction and adhesion process, impaction is just that the particle is flowing through the sand media, and it collides with one of the stationary sand grains. And adhesion, that's just another word for sticking. So that is the process that we are talking about when we talk about filtration in surface water treatment. And so, thinking about the exam and what you need to be able to do, you need to be able to explain the process of impaction and adhesion and kind of tell the story about a destabilized colloid particle that's flowing through the sand media and eventually comes to a sand particle that it impacts and it adheres to or sticks. So the water is suspending these very small particles that are smaller than the grains and smaller than the voids, but those particles still stick to the sand grains when they collide. So overall, the purpose of filtration is to try and get the water under this goal of 0.3 turbidity units. And there is the potential of a little bit of straining that happens, particularly when you use a multimedia filter. Ordinarily in water treatment, sand is doing most of the heavy lifting in terms of the filtration, but it is increasingly common to use different types of filter media where you maybe would have a layer of crushed coal on top of the sand, and then beneath the sand would be gravel, or there could be even plastic media that could be crushed, and because of the different density in coal, plastic, sand, and gravel, then they would naturally exist at different depths in the sand filter column. The way that we can classify filtration types is by how much we're loading water onto the surface area of the sand filter. And there are things that are called slow sand filters that you would purposely have kind of a scum layer building up on the front face of the sand when you have a really low loading rate. And that's a little bit leaning more towards straining than impaction and adhesion. When you have a high rate of loading with a lot of water going through the filter, then you're relying more on impaction and adhesion. So here's a cutaway view that shows what we have. And so we're looking at it from an angle, also from an elevated location. And so the water comes in to the sand filter, and there's a certain thickness of filter media. So here where it says filter media, that could be some crushed anthracite coal. It could be some sand. Beneath that, gravel supporting it. And generally, you'd have to have some sort of a porous block underneath it to support the weight, because it's going to be very heavy. It's going to have all of the weight of the media plus the weight of the water above it. So structurally speaking, there has to be kind of a strong surface for all of this to rest on. Eventually, the filter is going to get clogged. And so every few hours, they have to backwash the filter. And so they have to turn the water the other direction. And so instead of, normally under ordinary operating conditions, the water is going down through the sand filter. So we pour an excess of water above it, and you pool a certain amount of water above it so that there's a pore pressure. Let's see, I'm going to sneeze. Well, maybe not. You'd have a certain amount of water, that's right on the verge, right above the surface of the sand. And the higher the depth of the water above it, it's forcing the water through at a higher velocity, and you're overcoming the clogging of the filter. But eventually, when the voids between sand grains get completely full of the clay, then you have to stop loading water on top of it, and you start flushing it from below, and you are suspending it. So we're going to look at a little animation here. That illustrates the process. Okay, so we're starting with the water's coming in from the top of the clarifier. So here it's saying in from sedimentation tank. So there's a little bit of particles that escape being removed during the clarifying stage. And we've got some water on top of the sand. So here, this is just showing this is the water component of it. Here's the sand. Beneath that would either be like a crushed gravel or just something that the sand is resting on. And the sand traps those particles. Now eventually, the sand is too clogged. Like there's so many voids that are filled with the trapped particles that our head loss is increasing through the sand, which just means to get a certain flow rate through the sand, we're having to add more and more water to force it through. But eventually, you know, like all of the voids are getting clogged with it. And so there's this wash storage tank, which is a certain amount of water we keep in reserve, so that now we're sending water upward. So before you could see the arrow, the water's going down through the sand filter, out into this storage tank towards disinfection. But when the sand filter gets completely full, then we block it off. Here's this red thing showing the block. And we shake it loose. You suspend the sand, and it's kind of, the sand is fluidized, as it's called, a fluidized bed. And the sand grains are banging into each other, and it's kind of like a way of, if you've got a dirty rug, you shake it. You know, you'd go to the window and you'd shake the rug just to get all of the dust out of it, and then you take the rug back inside the house. And so during this process, the backwash stage, we're sending water up at a fast enough velocity that actually the sand is suspended, and it's kind of, the sand grains are banging into each other. So I guess it's more than just shaking the rug. It's like beating the rug with a stick to get all of the stuff off of it. So this diagram isn't showing that like there's a certain depth of water. Oh, maybe it is showing it. So look how thick the sand is. When they backwash, now it's thicker. Do you see how the brown layer is thicker? The reason why it's thicker is that when you turn the water around, you're blocking it, then you're fluidizing the bed. It's kind of like, I talked about skydiving in one of those stationary air tank chambers where they've got like the fan holding the skydiver at a constant elevation. So the water you'd send to backwash at a high enough velocity to kind of get that sand bed fluidized. You don't want to have so much velocity that the sand overflows. You just want to have it enough so that it kind of expands a little bit and is going through the backwash process. And you do it for 15 or 20 minutes, then you can close the valve again and restart operation during the filtering stage. So back to this diagram, these wash troughs, that's only used to collect the water during backwash. So the reason why you need an outlet at the top of the sand filter is to remove the dirty water during the backwash process. All of the clean water comes through the bottom of the sand filter. So any questions so far about sand filtration? Okay, this is showing a bit more about filter backwash and bed fluidization, where you'd have an elevated storage tank of water, elevated because you're going to need a fair amount of pressure to give you enough velocity to fluidize that bed. And so part of the design work that's done is making sure that there's enough distance between the sand layer and the overflow troughs so that the bed can fluidize and the turbidity that had been collected in the sand is shaken loose. And you know that it's time to backwash just when the flow rate of water through the sand filter starts decreasing, or when the depth of water required to push the water through the sand is going up. So during the backwash and bed fluidization, the particles, the sand particles, collide with each other, and all of the colloids that had adhered to the outside surface, they kind of slough off, and that water can get wasted. The overflow wash water is usually just disposed of. Sometimes a portion of it may be recycled back to the very beginning of the water treatment process if they're in a place where there's a water shortage and they don't want to waste any of it. So we classify sand filters into how much we load onto the surface of the filter. So by the way, when I talk about the surface area of the filter has a certain width, and so here's one dimension, the width, and it's got a certain length. Here's the other dimension. And so if we're looking down from above, the area that we're interested in is the top view area of sand. And it's not necessarily like the cross-sectional side view area of the sand, it's the top view that is the important thing in talking about loading rate. And so a slow filter is pretty uncommon these days. There's only a handful of communities that still have these old style slow filters, and the reason why they're not very common is they just use a lot of land area. If you, with a single square meter of sand, if you're only getting 2.9 to 7.6 cubic meters per day out of a square meter of sand surface area, then you'd need a lot of space for your sand filters. It's also kind of difficult in the case of slow filters because a scum layer accumulates on the surface of the sand rather than being impaction and adhesion. Slow filters generally are straining, and so instead of a backwash process, the way that they maintained slow filters is by scraping off the top layer of sand and just disposing of it. And so you've got some material losses associated with the slow filter. And so because of those two main disadvantages, that you're constantly losing sand and that the loading rate is so low, then rapid sand filters allow us to get the same level of quality in terms of the finished water turbidity, but they're relying on a different mechanism for removing the particles. It's impaction and adhesion. So a traditional rapid sand filter maybe would be as high as 120 cubic meters per day for every square meter of surface area. And there have been some rare applications where ultra-high loading rates of up to 135 cubic meters per day for every square meter of sand area have been used. So the way that we calculate the loading rate is the flow rate of the water that's being treated divided by the surface area of the sand filter. So this is sometimes called the face velocity or the loading rate. And if you look at the units, if you've got cubic meters per day divided by square meters, then that ends up having units of meters per day. And so that's why it's called the face velocity, is simply just because of the units canceling out the way they do to length per time. But maybe it's easiest conceptually to think of it as a flow rate per area of surface of the sand filter. One of the key considerations when it comes to designing sand filters is knowing that every once in a while you're going to have to take a filter offline for backwash. You may need to take a filter offline, for example, to service the pumps, to replace the sand media, some other kinds of repairs. And so it's always a good idea to build redundancy into your system. And there's an increasing discussion in our society these days of resilience. You know, the idea that you should have more than one way to provide for a necessary service. Like if you're on a spacecraft, you'd want to have more than one way to get oxygen. Because if the main thing breaks down, you want to have a backup. And so that principle is true on airplanes. It's true in water treatment systems. And so the way that comes into play in terms of filtration is you wouldn't just have one gigantic sand filter, because if you did, then when you need to backwash, you're not able to produce any water. So it's better, instead of having one gigantic filter, to break it into parallel components. That maybe if you had 6 sand filters, then that would allow you to have one of them down for backwashing, 5 in operation at any time, and so then you could rotate which of the filters is backwashing. If the backwash process takes 20 minutes and you can filter for 6 hours until it needs to be backwashed, then that would give you plenty of redundancy if you had 6 filters and 5 gave you enough production rate. So how many filters to install is a question for like what you think the low flow rate during the day would be, what you think the high flow rate during the day would be, how often you need to backwash, and just being prepared for breakdowns of equipment. The other thing that is considered when you're designing filters is just what size of sand grains to use, what other filter media like the coal and how finely crushed it is. The advantage of coal, by the way, is that it can remove dissolved organic materials. And so having a layer of coal in the water can make the water taste better, and it can remove potentially carcinogenic compounds like organic chemicals that got into the water because it's maybe pesticides that have run off, or things that like chemical spills that are unintentionally just somehow always getting into the water. A little bit of gasoline here, a little bit of motor oil there. If you've got crushed anthracite coal, then it can give you a level of protection against unintended organic chemicals getting into the finished water. So not all sand particles have the same size, and so there's going to be a variety of void sizes in the sand. And when you fluidize the bed during the backwash process, it's really interesting when they gradually decrease the velocity at the end of backwashing, then the heavy things settle first at the bottom of the filter, The large diameter sand grains will settle at the bottom of the sand column. The fine particles are at the top. So it's actually kind of the reverse of what we wish would happen. Like from a straining standpoint, it would be best if we had the fine sand grains at the bottom of the column of sand, so that you had a progressively smaller and smaller pore size as you had removed some of the turbidity but not yet all of it. But that's just not possible when you're backwashing the sand filter to clean it, and you're gradually reducing the backwash flow rate, just that the heavy particles settle first. And so having a variety of filter media densities is a way to get around that, where having the crushed anthracite coal on top, that's less dense than the sand grains, and you may have stones that are more dense than the sand grains, and that allows you to play around a little bit with the variety of density and sizes that can occur. So sand filters can sometimes be broken up into loading rate. So we talked about slow versus rapid. They can also be classified by whether you're using just a single media, like having only sand, or dual media filters if you had a secondary, in addition to sand, a secondary media like plastic or coal or gravel. Then you've got a greater utilization of the filter bed. Filter bed utilization is related to what I was mentioning earlier, that if it's only the top part of the sand that's actually doing the straining, that portion of it that is doing straining, then the sand below it isn't really having as much effect in the removal. So you get a more efficient removal by using a variety of filter medias. And so, this is a cutaway showing that having coal followed by a layer of sand and gravel is a pretty common setup. I've never visited a treatment plant that had plastic media, but the advantage of plastic obviously is that it has very low density, and so then if you had a fine layer of plastic on top of the coal, then that would be just another way of filtering out the colloid particles. But of course, people are getting increasingly nervous about microplastics. You probably hear a lot about that. People are switching to metal or glass water bottles so that they don't have exposure to the plastics. And so I would assume that they're out there, systems that rely on crushed particles of plastic at the top layer of the sand filter, but if they do exist, maybe people are starting to have second thoughts about those. Okay, so I've prepared this in-class exercise for you. Let me hand out the paper. We're going to do some calculations related to a sand filter and figuring out how many different sand filter boxes we should put into place. And what we know is that just based on the land that's available, we want them to be 7 by 7. 7 meters by 7 meters is the size. And we know the loading rate we're going to select here is 120 cubic meters per day per meter of surface area. So the question is, what is the overall surface area that's needed? How many sand filters would we need? But then starting to think about in terms of redundancy. So I'm stepping you through a couple of questions here, A through F. I'm going to pause and give you some time to do calculations and think through this process, and then we'll talk about it together. Okay, so if we're using 120 cubic meters per day per meter of filter area as our design standard, basically what I'm stepping you through in these calculations is just the process of thinking about, so how many filters do you need, and then should we round it to a certain number based on resiliency concerns. And so just looking strictly at the area of surface for the sand filter that's required, if we have 0.83 cubic meters per second, we have to multiply it by 86,400 seconds per day, and then divide by the 120 design parameter, and that says that there would be 597 square meters of surface area that's needed. And we're going to build these in 7 by 7 meter increments. And so each box is 49 square meters, and so that means that we'd have to get 12.2 filters. And obviously, we can't build 2/10 of a filter. We have to either build 12 or build 13. So if we round down and made 12 filters, each of them 49 square meters, then what that means for the loading rate is that the loading rate would be slightly higher than the limit of 120, which was our design guideline. 120 cubic meters per day per meter squared. So we're slightly above that, and maybe that's okay, maybe it's not. It's the sort of thing that you'd have to know more about the relationship between loading rate and finished water quality. Because if you increase the loading rate too high, the risk is just that some particles are going to get through. So it might be that exceeding the rate slightly wouldn't necessarily cause you problems. It's kind of a judgment call where more information is needed. But if we say that one of the filters, if we built 12 and one is taken offline for backwash, then that means the remaining 11 filters are having to carry this flow of 71,712 cubic meters per day, and it's on 539 square meters. That's the area associated with 11 of the 49 square meter filters. So that would mean a loading rate of 133 cubic meters per day per square meter of filter area. And this was saying during backwash the loading rate can be as high as 130. So 11 wouldn't really work for us necessarily. So, based on that limit, that would maybe argue that we need to use 13 filters total, because with having 12, let's say that put us under the limit of 121. 121 was the loading rate, and that's higher than the limit of 120. So just the idea of 13 filters would keep us under both the 120 limit during normal operations, and it would take us below 130 for during the backwash. So the last thing here about explaining what happens if you never backwash the filter, basically it would get clogged. I mean, the long and short of it is just that the particles that we're trying to remove would continue to accumulate between the sand grains in the voids until the voids are so small that the water has a hard time passing through the remaining spaces. And so the head loss through the filter would become really high, that you'd have to have a really deep column of water above the sand filter to push the water flow. So you wouldn't be able to achieve the required flow rates if you never backwash the sand filter. Okay, that's it. It's 1:50. We are out of time. Just as a revisiting of the announcements, remember that on Friday we've got our exam. So please be sure to prepare that equation sheet. You can put anything on it that you like. You can put concept definitions on there if you like, equations. You can put sample problems, reminders on how to solve things. Anything you like at all can go on that one-page front and back of notes.